So okay, we started in the last class. We defined the angular deformation rate. Then we went ahead and defined the irrotationality, the vorticity vector, and then we were in the process of discussing the stream function. Okay, so we assumed that a two-dimensional flow which is incompressible, and if the flow is incompressible, we know that the equation of continuity is given by del u del x plus del v del y equal to 0. And now the thing is that if you have the continuity equation like this, so in that case, actually you can define a function psi equal to psi xy such that this psi satisfies these two conditions. What are the conditions? The conditions are that if you differentiate psi with respect to y, that is equal to the x component of the velocity, and if you differentiate psi with respect to x, that will be equal to the negative of the y component of the velocity. So if you choose psi in such a way, then what you will observe that this equation of continuity is getting satisfied automatically, which we have shown here. So this equation of continuity will be satisfied automatically. So such a function which satisfies these conditions and satisfies the equation of continuity automatically, that such a function is actually known as the stream function. Okay, so this is what we actually discussed towards the end of the last class. Okay, so psi equal to psi xy, we defined it to be the stream function of the flow, you can say, of the flow. Now why we are calling it stream function, why not something else? Because let us discuss it further, and we will be able to identify why it is called a stream function and why not by some other name. So in order to understand that why it is called a stream function, let us consider psi xy equal to, let us say, some constant. So what is the psi xy equal to constant? Geometrically, what does it represent? What is the geometrical interpretation of psi xy equal to constant? Is there anyone? ये क्या represent करेगा? Psi xy equal to constant is actually a family of curves. Okay, for example, let us say x square plus y square equal to constant. This is a family of circles. You change c, you will get a different curve. Okay, so psi xy equal to constant, in general, it represents a family of curves. Now let us proceed further. So if psi is equal to constant, then obviously d of psi will be equal to how much? How much it should be?
0.
It is 0. So d of psi is equal to 0. That is, total differential is equal to 0. So now if you proceed further and if you apply the definition of this d of psi, so this is del psi del x dx plus del psi del y dy equal to 0, because psi is function of x and y. So d psi will be equal to this much, and you already know that psi satisfies this condition, that del psi del x is equal to minus v and del psi del y is equal to u. So del psi del x is equal to minus v, so this is minus v dx plus del psi del y is equal to u, so this is u dy equal to 0. So what do you get from here? If you if you look at it, if you manipulate it, it is actually dx upon u equal to dy upon oh sorry v, dy upon v. So dx upon u, dy upon v. What is this actually? What is this? Have you read this? Have we already discussed this equation? What is this equation? This is actually equation of streamlines. ये हमने पढ़ा है ना कि dx upon u, dy upon v equal to dz upon w is equal to the streamlines, equation of streamlines in 3 dimension for a 3-dimensional flow. So because here you are considering only a 2-dimensional flow, so dx upon u equal to dy upon v. So this is nothing but actually a streamlines. So if you look at it in the reverse way, so this is your equation of a streamline and this is your solution. Okay, if you solve this dx upon u, dy upon v, you will be getting psi xy equal to constant. So it means what? This means what? This means what? Psi xy equal to constant is geometrically representing the streamlines of the flow. Is geometrically representing the streamlines of the flow. Is that fine? So so it means what? It means what? If you choose psi in such a way that it satisfies these two conditions, that del psi upon del y equal to u and del psi upon del x equal to v, sorry, minus v, then your equation of continuity will automatically be satisfied. And if you plot the psi xy equal to constant curve, those curves are actually the streamlines of the flow. Streamlines of the flow. So this actually this is what we have. Okay, so that is why, because the psi xy equal to constant represents the streamlines of flow, therefore the function psi is actually known as a stream function. Okay, because it gives you the streamlines of the flow. So I hope it is clear to everyone. So for a 2-dimensional flow, you can discuss like this. However, even if you have a 3-dimensional flow, the stream function exists. It is not like that it doesn't exist. It exists. But this kind of discussion may not be valid in that case, because psi xy equal to in that case psi may be function of x, y, z actually. Okay, so this discussion that del psi upon del y equal to u and del psi upon del x equal to minus v, this type of discussion is only valid when you have a 2-dimensional flow. Okay, so otherwise for a 3-dimensional flow, this type of discussion may not be valid, but still the stream function exists. It is not like that the stream function doesn't exist and streamlines doesn't exist. They do exist, but this discussion is particularly valid for 2-dimensional flow. That is why we have considered it that we are considering a 2-dimensional and incompressible flow. Okay. Okay, let us go ahead and let us discuss a different case. So this was, let us say, this was one case. Let us discuss another case. And let us consider that we have an irrotational flow. irrotational flow. I'm not telling whether it is two-dimensional or three-dimensional, but I'm telling it in general that it is a irrotational flow. So if it is an irrotational flow, then in that case, we know that since flow is irrotational, so we know that curl of Q will be equal to zero vector. Is that fine? Any doubt in this? For an irrotational flow, curl of Q is equal to zero vector. Now, we know from vector calculus that we know that if phi x y z is a scalar function, if phi x y z is a scalar function, then curl of gradient phi is equal to how much?
Zero. Sir, zero.
Can you tell me? Zero vector. Is that fine? So if phi is that, yes, it is zero. Now the thing is that your flow is irrotational. ध्यान देना, it is irrotational. So if it is irrotational, you already half of Q.
हेलो सर, आपकी आवाज ब्रेक हो रही है.
Yes, tell me. आज ना इंटरनेट का इशू है थोड़ा यहाँ पर, इसीलिए मुझे कनेक्ट करने में भी डिले हुआ. तो मे बी देर इज द स्पीड इज लेस टुडे. आई डोंट नो what is happening. So if you are finding it very difficult to understand, then I will stop. Otherwise, maybe if it is understandable, we can continue.
अभी ठीक आ रही है.
अभी ठीक आ रही है?
Yes sir.
ठीक है. So this is the case actually. Okay. Now, so it means what? It means if your flow is irrotational, this implies if the flow is irrotational, there exists a scalar function, say phi xyz, such that are you happy with this? Is that okay? Any doubt in this? If you have any doubt, please discuss. बताओ भाई, Q इक्वल टू ग्रेडियंट ऑफ फाई लिख सकते हैं या नहीं?
Yes, sir.
Because we already know that if from vector we have a curl of gradient phi equal to 0. We already know this this result. Now, for irrotational flow, we know that curl of Q equal to 0. It means some some of some scalar function, we are assuming Q equal to gradient of phi. So from here, actually, you can say that uh, uh, you can say that this is U V W is equal to, and what is gradient of phi? Gradient of phi is nothing but del phi del x, del phi del y, del phi del z. Okay. So in that case, if you compare the components, you will be able to find out U equal to del phi by del x, V equal to del phi by del y, and W equal to del phi by del z. Okay. So it means what? If the flow is irrotational, then in that case, there exists a function phi such that if you differentiate that function phi with respect to x partially, that will be equal to the x component of the velocity. If you differentiate that function with respect to y partially, that will be equal to the y component of the velocity. And similarly, if you differentiate that with respect to z partially, that will be equal to the z component of the velocity. That is UVW. You can obtain by partially differentiating the function phi with respect to x, y, z. This phi is actually known as velocity potential. Okay, this is called, the function phi is called, the function phi is called velocity potential. It's called velocity potential. Okay, it's called velocity potential. And now, if your motion is irrotational, if your fluid flow is irrotational and fluid is inviscid means non-viscous, then in that case, that kind of flow will always be irrotational flow. So if I'm writing it here, if the motion is irrotational, okay, and fluid is inviscid, तो एक्चुअली हो क्या रहा है कि हम क्या अज्यूम कर रहे हैं कि मोशन जो फ्लो है वो इरोटेशनल फ्लो है और फ्लूइड जो है इनविसिड है. तो अगर फ्लूइड जो है इनविसिड हो गया, इट मींस देयर इज नो विस्कोसिटी, and if there is no viscosity, there will be no shear forces acting on the fluid elements or fluid particles. So if there are no shear forces acting on the fluid particles and the motion is already rotational, it means that there are no chances that this flow will become rotational. ओके, सो एक बार अगर इरोटेशनल है और फ्लूइड इनविसिड है, तो कोई भी इनविसिड फ्लूइड जिसका मोशन अगर इरोटेशनल है, ठीक है, सो दैट विल ऑलवेज बी इरोटेशनल. उसका रोटेशनल होने का कोई मतलब चांसेस नहीं है, बिकॉज द फ्लूइड इज ऑलरेडी इनविसिड फ्लूइड. सो इफ देयर आर भाई रोटेशनलिटी आता कहां से है? रोटेशनलिटी आएगा तब जबकि शियर फोर्सेस लगेंगे. तुमने देखा कि एंगुलर डिफॉर्मेशन कैसे होता है, तो एंगुलर डिफॉर्मेशन का जो रीजन है वो है शियर फोर्सेस. तो शियर फोर्सेस के कारण एंगुलर डिफॉर्मेशन हो रहा है और एंगुलर डिफॉर्मेशन के कारण ही तुम्हारा रोटेशनलिटी आ रहा है. तो अगर shear force लगेगा ही नहीं, जो क्यों नहीं लगेगा, क्योंकि इनविसिड फ्लो है, इनविसिड फ्लूइड है। तो अगर इनविसिड फ्लूइड है तो shear force नहीं लगेगा, और shear force नहीं लगेगा तो एंगुलर डिफॉर्मेशन नहीं होगा। तो अगर एंगुलर डिफॉर्मेशन नहीं होगा, इन दैट केस अगर फ्लो तुम्हारा इनिशियली इरोटेशनल हो जाता है तो वो हमेशा ही इरोटेशनल रहेगा। ठीक है, so that is actually the conclusion. So if the motion is irrotational and fluid is inviscid, then the motion always remains irrotational, always या फिर then the motion remains always irrotational. ओके okay? तो ऐसा फ्लो जो कि हमेशा इरोटेशनल रहता है उसको बोलते हैं पोटेंशियल फ्लो। Such a flow is called potential flow. ठीक है ना, सच ए फ्लो इज कॉल्ड पोटेंशियल फ्लो। सो देखो हम धीरे धीरे चीजें डिफाइन कर रहे हैं। पहले हमने रोटेशनलिटी डिफाइन किया, वॉर्टिसिटी वेक्टर डिफाइन किया, उसके बाद स्ट्रीम फंक्शन डिफाइन किए, उस स्ट्रीम फंक्शन से स्ट्रीम लाइन को रिलेट किया। अब हम इरोटेशनलिटी को यूज करके वेलोसिटी पोटेंशियल डिफाइन कर रहे हैं, और उसके बाद हम पोटेंशियल फ्लो भी डिफाइन कर दिया। ठीक है ना, नाउ दिस इज व्हाट एक्चुअली वी हैव। सो नाउ द थिंग इज दैट what happens, or what is the relationship between this velocity potential and the stream function? Okay, so obviously when we are saying that a stream function, and we want to utilize the discussion that we have already made, so let us consider that the flow is two-dimensional. Okay, and let us proceed further. So we are trying to establish a relationship between the stream function and velocity potential, क्योंकि velocity potential भी देखा जाए तो अगर ये तो थ्री डायमेंशनल के लिए हमने लिया था, ठीक है ना, थ्री डायमेंशनल में हमारा velocity potential जो है वो एक्स वाई जेड का फंक्शन है। ठीक है, अगर टू डायमेंशन का velocity potential होगा तो कैसा होगा, वो एक्स और वाई का फंक्शन होगा। ठीक है ना, सो अगर फाई ऑफ एक्स वाई वेलोसिटी पोटेंशियल है किसी टू डायमेंशनल फ्लो का, तो फाई एक्स वाई इक्वल टू कांस्टेंट विल गिव यू अ फैमिली ऑफ कर्व्स like psi xy equal to constant. So because phi xy equal to constant gives you a family of curves, and psi xy also gives you a family of curves, we are trying to establish a relationship when both exist together. Okay, when the velocity potential and stream function exist together for a flow, then what is the relationship between them? So that is what we are trying to find out. So let us now consider, let us consider a two-dimensional incompressible and irrotational flow. ठीक है ना, ध्यान दो कि हम कैसे कैसे आगे बढ़ रहे हैं। सबसे पहला जो हमने डिस्कशन किया उसमें हमने अज्यूम किया था कि लेट अस अज्यूम दैट द फ्लो इज टू डायमेंशनल एंड इनकम्प्रेसिबल। तो टू डायमेंशनल और इनकम्प्रेसिबल होगा तो उसके लिए ये डिस्कशन वैलिड है, और स्ट्रीम फंक्शन डेफिनेटली एग्जिस्ट करेगा। ठीक है ना, उसके बाद हमने अज्यूम किया कि लेट अस अज्यूम दैट द फ्लो इज इरोटेशनल। तो अगर फ्लो इरोटेशनल होगा तो वेलोसिटी पोटेंशियल एग्जिस्ट करेगा। ठीक है ना, अब हम चाहते हैं कि दोनों साइमल्टेनियसली एग्जिस्ट करे किसी फ्लो के लिए। तो दोनों साइमल्टेनियसली एग्जिस्ट करेगा मतलब वेलोसिटी पोटेंशियल भी एग्जिस्ट करे और स्ट्रीम फंक्शन भी एग्जिस्ट करे। तो दोनों के साइमल्टेनियसली एग्जिस्ट करने का कंडीशन क्या होगा कि फ्लो जो है वो टू डायमेंशनल हो, उसके बाद इनकम्प्रेसिबल हो, और उसके बाद इररोटेशनल हो। तो ये तीनों कंडीशंस हमने अज्यूम कर लिए कि लेट अस कंसीडर अ टू डायमेंशनल इनकॉम्प्रेसिबल एंड इरोटेशनल फ्लो. ठीक है. So if this is the case, it means what? It means what? Therefore, the stream function psi exists. The stream function psi equal to psi xy and velocity potential phi equal to phi xy both exist together. ठीक है ना? I hope it is clear to everyone. Now the thing is that it means what? So it means what? The stream function and velocity potential both exist together. So it means what? Psi equal to constant are the stream function. Constant are the stream function, streamlines or ठीक है. So this implies d psi equal to 0. So this implies what? This implies कि minus v dx plus u dy equal to 0. ठीक है. I hope it is clear to everyone. And from here, actually, what you can conclude that dy dx equal to v by u. V by u. V upon u. So what is dy dx? Can you tell me? What is dy dx of this psi equal to constant? So this psi equal to constant is your actually family of curves. Okay, and this is your differential equation from where you are getting this solution. So it means what? Dy dx is the slope of the this psi equal to constant family of curves. Okay, so it means what? It means what? This is nothing but this is slope of psi equal to constant. This is slope of psi equal to constant. So actually we are trying to find out what happens with psi equal to constant and phi equal to constant. So let us say this is 1, and similarly phi equal to constant will give you d phi equal to 0. And if it is d phi equal to 0, it means what? It is del phi del x dx plus del phi del y dy equal to 0. I hope it is clear. So this is actually equal to del phi del x equal to u dx by the definition of velocity potential plus v dy equal to 0. And from here, actually, you can find out the slope of phi equal to constant. So the slope of phi equal to constant equal to minus u upon v. So this is actually, let us say, this is actually the slope of phi equal to constant. So now what do you observe actually? What do you observe from equation 1 and 2? From equation 1 and 2, you can observe that from 1 and 2, you have dy dx of psi equal to constant multiplied with dy dx of phi equal to constant equal to how much?
Minus
How
1.
much is this? This is minus 1. So what is the conclusion now? Can you tell me the conclusion?
Orthogonal.
Sir, perpendicular.
Yes.
Perpendicular.
Yes. Orthogonal. Actually, psi equal to constants are the streamlines. They are actually family of curves. Phi equal to constant also are family of curves. Okay. Now the thing is that if both of them exist together for a flow, if both of them exist for a flow together, then in that case, at a common point where phi equal to constant and psi equal to constant intersect, the angle is actually pi by 2. They intercept each other at 90 degrees. So this implies so this is valid when this is valid provided 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 uv not equal to 0. That is uh, that is this intersection is happening where there is no stagnation point. So at that point, that is, the point is not a stagnation point. Otherwise, the slopes will not be valid. Stagnation point. So this implies what? This implies that the slope of the tangents to the curves, to the family of curves, in fact, family of curves, what are the curves? Psi equal to constant and phi equal to constant. The slope of the tangents to the curves, to the family of curves, psi equal to constant and phi equal to constant, are perpendicular at the point of intersection. At the point of intersection, are perpendicular to each other, and this implies the curves psi equal to constant and phi equal to constant are orthogonal. Orthogonal to each other. Orthogonal to each other. Is that fine? ठीक है. So ये actually ऐसा चीज है कि let us say you have let us say this is your phi equal to constant. Let us say phi equal to k1, phi equal to k2, phi equal to k3, phi equal to k4 and so on. ठीक है. और psi equal to constant अगर होंगे तो psi equal to constant कैसे होंगे? So let us say like this. ठीक है. उतना अच्छा ड्रॉ नहीं हो रहा है, but actually wherever there is a point of intersection, this is 90 degree. ठीक है. These are all 90 degrees. ठीक है. So this is psi equal to, let us C1, psi equal to C2, psi equal to C3 and so on. So this is the situation. So they are orthogonal to each other. I hope it is clear to everyone. Any doubt in this?
No, sir.
Okay, so now let us go ahead and try to note down a very important result. So अगर फ्लो तुम्हारा यही अजम है. So two-dimensional incompressible flow. If the flow is two-dimensional and incompressible, we already know that if the flow is two-dimensional and incompressible, then obviously you have u equal to del psi by del y and v equal to minus del psi upon del x. ठीक है ना? This is actually we already know, because the stream function will exist and this will satisfy these two conditions. So if the flow is two-dimensional and incompressible, हम इसके आगे और फर्दर हमने इसमें क्या अज्यूम कर रखा है कि if the flow is irrotational also, if the flow is irrotational also, rotational, if the flow is irrotational, in that case, अब ये टू डायमेंशनल फ्लो है, तो टू डायमेंशनल फ्लो है तो रोटेशन होगा तो किसके अबाउट होगा, कौन से एक्सिस के अबाउट होगा, बताओ? जो स्ट्रीम फंक्शन तुमने लिया है वो ऐसा चूज किया है कि u इज डेल साई अपॉन डेल y एंड v इज माइनस डेल साई अपॉन डेल x, and you are telling that the flow is two dimensional and it is irrotational now. So obviously it has to be, अगर रोटेशनल होता तो किस एक्सिस के अबाउट होता,
जेड एक्सिस,
जेड एक्सिस के अबाउट होता ना. तो इफ द फ्लो इज irrotational it means what, angular velocity along z axis is 0. Is that fine? Omega z equal to 0. ठीक है? Any doubt? So if omega z is equal to 0, you can recall that what we had in that case, omega z is equal to del v del x minus del u del y. Here it is. Del v del x minus del u del y. So del v del x minus del u del y equal to 0 if the flow is irrotational. I hope it is clear. ठीक है? अब हम तो अगर फ्लो इरोटेशनल है तो डेल वी डेल एक्स माइनस डेल यू डेल वाई इक्वल टू 0 होना चाहिए, और हमारा u कितना है, डेल साई डेल वाई, और v कितना है, माइनस डेल साई डेल एक्स. ठीक है? सो अब डेल वी डेल एक्स निकाल लो यहां से और डेल यू डेल वाई निकाल लो यहां से. तो दोनों को निकाल के सब्स्टिट्यूट करोगे तो साई के फॉर्म में तुम्हारा इक्वेशन आएगा, और साई के फॉर्म में क्या आएगा, डेल स्क्वायर साई डेल एक्स स्क्वायर प्लस डेल स्क्वायर साई del y square equal to 0. Is it okay? Any doubt? What is this equation called?
Laplace equation.
Yes. So it is actually Laplace's equation in two dimensions. ठीक है? इसको हम लोग del square psi भी लिख सकते हैं, अगर हम मान के चले कि टू डायमेंशन को हम इस तरह से लैप्लासियन फॉर्म में लिख सकते हैं. ठीक है ना? तो डेल स्क्वायर साई इक्वल टू 0. सो इट मींस व्हाट कि अगर फ्लो जो है वो टू डायमेंशनल और इनकम्प्रेसिबल है और फर्दर इट इज आल्सो इरोटेशनल, सो टू डायमेंशनल, इनकम्प्रेसिबल एंड इरोटेशनल फ्लो में जो स्ट्रीम फंक्शन है वो लैप्लास इक्वेशन को सेटिस्फाई करता है. आई होप इट इज क्लियर टू एवरीवन. एनी डाउट? ठीक है ना? So this is actually your one point. The other point I'm telling you, let us suppose let the flow is irrotational. So if the flow is irrotational, it means you have velocity potential existing. So u equal to del phi del x, v इक्वल टू डेल फाई डेल वाई, ठीक है ना। और ऑब्वियसली W इक्वल टू डेल फाई डेल जेड होगा, बट उसका यूज हम नहीं करेंगे, इसलिए उसको लिख नहीं रहे हैं, ठीक है। सो फॉर ए फ्लो, लेट द फ्लो इज इरोटेशनल, देन यू हैव u डेल फाई डेल एक्स v इक्वल टू डेल फाई डेल वाई। अब हम इसमें दो चीज और ऐड कर लेंगे कि इफ इट इज टू डायमेंशनल एंड इनकम्प्रेसिबल, सो टू डायमेंशनल इनकम्प्रेसिबल अगर होगा तो क्या होगा, कंटिन्यूटी इक्वेशन टू डायमेंशनल इनकम्प्रेसिबल फ्लूइड का डेल यू डेल एक्स प्लस डेल वी डेल वाई इक्वल टू 0। Now you already have u equal to del phi del x and v equal to del phi del y. So if you substitute it here, you will find out del square phi del x square plus del square phi del y square equal to 0. So this means what? This means what? Laplacian of phi is equal to 0. So it means what? It means what? If the flow is irrotational and it is further two-dimensional and incompressible also, then your velocity potential actually is satisfying the Laplace's equation. So it means what? It means what? We actually got two important results. If the stream function and velocity potential, they exist together. So when do they exist together? They exist together when the flow is two-dimensional, incompressible, and irrotational. Okay.
हेलो सर। सर
Yes.
आपकी स्क्रीन नहीं दिख रही है।
स्क्रीन नहीं दिख रही है?
सर
नहीं
दिख रहा है,
सर।
उसके नेटवर्क इश्यूज होंगे। दिख रहा है।
दिख रहा है ना?
यस सर, यस सर।
सर अभी दिख रही है, ठीक है।
ठीक है. So I was telling that when the stream function and velocity potential both exist together, when they do exist together, whenever your flow is two-dimensional, irrotational, and incompressible, these three conditions are satisfied. If these three conditions are satisfied together, then your psi exists, your phi exists, and whenever they exist together, then they satisfy the Laplace's equation. Psi will satisfy Laplace's equation, and phi will also satisfy Laplace's equation. Is that fine? Further, the family of curves psi equal to constant and phi equal to constant, they intersect each other at right angles. Okay, so that they are actually orthogonal family of curves. These are the two important conclusions that we can conclude from today's discussion. Okay, so it means what? Now we can write down here that for a two-dimensional, incompressible, and irrotational flow, incompressible and irrotational flow, phi and psi satisfies Laplace's equation. That is, whenever phi and psi exist together, whenever phi and satisfy exist together, they satisfy the Laplace's equation. ठीक है? They satisfy the Laplace's equation. I hope it is clear to everyone. Whenever phi and psi exist together, they satisfy Laplace's equation. और यहाँ पर था कि whenever phi and psi exist together, they are actually orthogonal to phi equal to constant and psi equal to constant are orthogonal to each other. So I hope it is clear to everyone. Any doubt in this?
No sir.
Okay, so let us proceed further and let us take an example. So this is a question, and test whether the motion specified by q equal to k square. K square is some constant actually, xj minus yi x square plus y square, where k is a constant. K is constant. ठीक है? Is a possible motion for an incompressible fluid. Motion for an incompressible fluid. ठीक है? तो पहला पार्ट ये है कि टेस्ट whether the motion specified by this. So what is this? Q vector equal to k square x j cap minus y I cap upon x square plus y square. So this is actually a velocity vector. Okay, this is a velocity vector that is given, or let us say that I'm not telling it velocity vector. Let us suppose that this is any vector which is given, because velocity vector बोलने का मतलब है कि already इससे velocity हो रहा है. ठीक है ना? तो हम ये मान के चलते हैं ये एक वेक्टर है. Question is that show that or test whether this is a possible motion for an incompressible fluid or not. मतलब कि इस velocity vector से, इस वेक्टर से, जो गिवन वेक्टर है, इस वेक्टर से कोई मोशन हो रहा है कि नहीं हो रहा है. मतलब इज इट अ पॉसिबल वेलोसिटी वेक्टर फॉर ए फ्लूइड मोशन, इनकम्प्रेसिबल फ्लूइड मोशन. दिस इज व्हाट वी नीड टू टेस्ट. ठीक है? तो सबसे पहला काम हमारा है कि ये चेक करना कि ये एक वेलोसिटी वेक्टर हो सकता है कि नहीं हो सकता है. ठीक है? For an incompressible fluid. So for an incompressible fluid, what we should check whether in order to identify whether it is a possible fluid velocity vector or not, what should we check? So इसमें मैं लिख रहा हूं. ठीक है? तुमको याद रहेगा इससे. So in order to test whether the given function, the given vector is a possible velocity vector for an incompressible fluid motion, in order to test whether the given vector is a possible velocity vector for an incompressible fluid motion, we need to check the continuity equation. The इक्वेशन सेटिस्फाई कर जाएगा तो मोशन हो रहा है. अगर कंटिन्यूटी इक्वेशन सेटिस्फाई नहीं करता तो मोशन नहीं हो रहा है. ठीक है? कंटिन्यूटी इक्वेशन फॉर एन incompressible fluid. I hope it is clear. ठीक है? So this actually you can write in some note. This is not the part of solution. Even if you not, even if you don't write this in the solution, there is no problem. Okay. So now we have. So for solution, we have Q equal to K square X j cap minus Y I cap divided by X square plus Y square. So if you want, you can write down this as K square X upon X square plus Y square j cap minus K square Y upon X square plus Y square I cap. It means what? It means what? This is your V component because it is appearing with j cap, and this is your U component which is appearing with I cap. So U equal to minus K square Y upon X square plus Y square, and V equal to K square X upon X square plus Y square. I hope it is clear. ठीक है? अब तुमको सिर्फ चेक कर लेना है कि कंटिन्यूटी इक्वेशन फॉर एन इनकम्प्रेसिबल फ्लूइड सेटिस्फाई कर रहा है कि नहीं है. सबसे पहले बात बताओ कि इसमें दो ही कंपोनेंट दिए हुए हैं, तो हमको टू डायमेंशनल कंटिन्यूटी इक्वेशन चेक करना है. मतलब यू नीड टू चेक डेल यू डेल एक्स प्लस डेल वी डेल वाई इक्वल टू 0. ठीक है? आई होप इट इज क्लियर. So now in order to test the continuity equation, let us assume that, just for the sake of simplicity, otherwise there is no reason to denote like this. So x square plus y square equal to r square. Let us assume. So this implies what? This implies 2x equal to 2r del x. Is that okay? So this 2x 2 will cancel out, and del r del x equal to x by r. ठीक है ना? Del r del x equal to x by r. Similarly, del r del y equal to y by r. ठीक है ना? ये रिजल्ट्स अपने पास रख लो. नाउ वी नीड टू चेक del u del x. सो del u del x. ठीक है ना? So you have del u del x equal to minus del x of k square y by r square. I hope it is clear to everyone. Any doubt in this?
No, sir.
So this is minus del. Let us differentiate this partially with respect to x. So if you differentiate this, so you have minus k square y will be outside, and I'm differentiating this 1 by r square with respect to x. So this is minus 2 by r cube, and then del r del x. So del r del x is actually x by r. So if you look at this, this is nothing but 2k square xy upon r to the power 4. I hope it is clear. Similarly, del v del y is equal to del y of k square x upon r square. ठीक है ना? सो अब इसको पार्शियली विथ रिस्पेक्ट टू y डिफरेंशिएट करो, तो k स्क्वायर x तो आउटसाइड आ जाएगा, or this is minus 2 by r cube del r del y. So that is y by r. So if you look at this, this is nothing but minus 2k square xy upon r to the power 4. So if you add del u del x and del v del y, now if you add del u del x and del v del y, that is del u del x plus del v del y, you actually get 0. This implies the equation of continuity is getting satisfied. ठीक है? Hence, q vector is a possible velocity vector for the motion of an incompressible fluid. I hope it is clear to everyone. Any doubt in this?
No, sir.
So we'll continue this in the next class, and we'll take some more examples related to this discussion what we have already discussed. Okay, and meanwhile you can go ahead and solve the problems available in your assignment. So whatever you can solve, and tomorrow we have research conclave, so maybe I will be busy in that. So let us see if we can take tomorrow's class, if we can conduct. So actually 25th, 26th and 27th, we have research conclave where all the research scholars, PhD students will present their work in the form of posters. So I'm a member of that committee, so I will be busy in that. अगर टाइम मिल गया तो मैं क्लास लूंगा, अदरवाइज ऐसे भी कल का ट्यूटोरियल क्लास होता है तो चल जाएगा. ठीक है. Roll number 1.
Yes, sir.
2.
Present, sir.
3.
Yes, sir.
4.
Present, sir.
5. 6. 7. 8.
Yes, sir.
9.
Present, sir.
10.
Yes, sir.
11. 12. 13.
Present, sir.
14. 15.
Present, sir.
16.
Present, sir.
17.
Yes, sir.
18. 19.
Yes, sir.
20. 21.
Yes, sir.
22.
Yes, sir.
23.
Yes, sir.
24. 25. 26. क्या आज कुछ ज्यादा ही लोग एब्सेंट हैं? 11-12 लोग एब्सेंट है. 1 2 3 4 5 6 7 8 9 11 लोग एब्सेंट है. 50% के लगभग एब्सेंट ही रहते हो तुम लोग. पता नहीं क्या कर रहे हो घर पे बैठ के. Okay, so let us close to, today's lecture. We'll continue this in the next class. Okay, so bye.
Thank you, sir.